Okay.
So, last time you spoke about quadratics mostly in terms of how to graph them, which is something you had to do on the test. I want to actually talk about graphing things in general now. But before that, we need to cover some previous ground. So maybe start with transformations of functions. And you don't need to know this in a crazy amount of detail. You just need to know how certain arithmetic operations affect the graphs of functions. So we're going to look at these especially in terms of graphing. And so how I want you to think of transformations, there are a few of them. So let's say we have, let's talk about the kinds of transformations we have. Transformation, in terms of a picture, is going to be either a reflection. Okay, so that means you're reflecting some mirror image, so you can have, I don't know, a triangle. You reflect it over here, and you obtain this other triangle. You can have a rotation. So you can talk about, okay, here's an object here, and you rotate it by some angle, and you end up with the object here. So by some angle theta. You can have what's called a stretching or a shrink. Some people might call this dilation. So you can have an object that's like this, and then you kind of stretch out the object, make it larger or smaller. You can also have what's called a shear. And this basically means, so let's say a rectangle was your original object. Basically means you change one of the axes at an angle. So you can imagine that the y-axis is leaned, but you still want to maintain the same shape. So a rectangle would become a parallelogram. So it's like you slide it. Right? And you have all these kinds of things that we can do, and they have many applications, which we're not going to see any of them in pre-calc, so let's not even worry about it. But there are certain things we can do to pictures in the plane that have a lot of meaning. And it turns out that all of these things, there's actually a mathematical background to them. We can actually do all of these by doing mathematical operations on the formula for the functions that give the graphs. So in that sense, let f of x be a function. Here are the transformations of f. So we can talk about, let's do reflections first. Okay. So that means like you're flipping a mirror image. There are a few reflections that you need to know about. One is multiplication by a negative sign outside the function. Right? Another one is a multiplication inside the function. Now each of these do a different thing. Do you remember what this does? Yeah?
Reflects about the x.
Reflecting the x-axis. So this flips something upside down. So that means it was here. That was its first state. And then it'll flip to here. That's the second state. So you can think of this as y equals x squared. Think about what y equals minus x squared would look like. It's a reflection in the x-axis. So if I have a picture and I want to flip it upside down, multiplication by -1 on the formula for that function will actually do that. This one, quite the opposite. Well, not the opposite. It's a reflection in the y-axis. So let's say the function was here. That was its first position. Then if I change all x coordinates in there to their negatives, I would get that as the second position. This is a reflection in the right. So you can think of this like f of x equals x squared versus minus f of x equal to minus x squared. So multiplying the outside of a function flips it in the horizontal axis. And here, well, the example I was thinking of in my head was x cubed. And here we're looking at f of minus x, which is minus x cubed, would look like the second one. So these are how we can get reflections. It turns out that having a picture flip turns out it's multiplication by a constant, in some sense the negative of constant. Someone stole the eraser again. You know I brought an eraser, but now I don't remember where I put it. Gotta be prepared for anything. Professor, I didn't know you were going to put that question on the test. You should have been prepared. Right? See, be prepared for anything. Although, to be fair, I put exactly on the test what I said I would. And if you did the review, it should have been easy. But that's another story. I haven't finished grading them, but yeah. I pretty much copied some of the review questions, and then I changed the function in the question. So it's pretty much it was the same thing. Anyway, let's continue. So these are reflections. You can also do some things that we care about are stretches and shrinks. So you can talk about the vertical one. So this is if you multiply a constant by x, and your k is some constant larger than 1, this stretches vertically. By a factor of k. If you take f of x and you divide it by that, it will shrink it vertically. So you can imagine a graph here. Looks like this. Let's say the height is 1, the bottom is -1, then it's going to stretch it so that the height goes up to k. So it'll do a vertical stretch of your picture, whereas this one would do a vertical shrink of your picture. So if this was here, that goes up to 1, then it'll just shrink it down so that this is 1 over k. You can also do horizontal stretch, shrink. So, one thing you want to notice is that when you're affecting the x, things often work in the opposite way that you would intuitively think. So if you multiply all x values by something larger than 1, like you multiply all of them by 3, it actually shrinks, not stretches. And if you divide each x by a number, that actually creates a stretch. So for example, if I had, say, this sort of function here, and so that's f of x, I can look at what, say, 2 f of x would look like. Now you multiply by 2, but it'll actually shrink the graph horizontally. So it happens in 1/2 of what it did before. Whereas if over here I had a graph which horizontally went up to 1, then if I divide by 2 in the x, sorry, this should be this f of 2x. Now if I divide by 2 in the x, it turns out that this is actually going to stretch it to be double. Okay, so when you're affecting the x, things often work horizontally in a non-intuitive way. So you just need to remember that. When you're affecting the y, things work kind of how you expect. If you're multiplied by something bigger than 1, you should stretch to something bigger than 1. If you divide by something bigger than 1, you should shrink to something. Well, the opposite happens when you're affecting the x, so that's something you need to remember. Because what happens here is that your outputs are the same, so your inputs have to compensate. So your x has to get larger to give you the same y value. And so what happens is you never achieve that y value until you get much further out, and then it kind of does the opposite. So those are stretches. You also need to know about shifts. So again, you have vertical shifts. And so this is if you take f of x plus some constant, and I'm assuming this is a positive thing, then this shifts up by k units. Take f of x minus a constant, this shifts down by k units. Again, here you can think of the x squared graph. So y equals x squared. You can compare that to something like y equals x squared plus 1. That's a shifting up. Whereas again, here, if I think of y equals x squared, I can compare that to y equals x squared minus 1, and that shifts down. Of course, ultimately, the whole point of this is for you to have some sort of intuition when you're graphing things. So you should know, oh, adding something, if I know this graph, I'll automatically know any graphs like these. Without too much work. I don't have to plot pretty much any points at all. If I know this original, I'll automatically know how to plot that plus any number. I'll automatically know how to plot that minus any number. You also have the horizontal shifts. So this is like f of x plus a positive number versus f of x minus a positive number. This one shifts to the left. So I know, like I said, whenever you're affecting the x, it kind of is counterintuitive. You think of adding in the x as moving to the right. Well, the thing is, if you add something to get the same output, your x has to get smaller to give you the same output, because you're now adding something to it. So it shifts to the left by k units. And you can think of comparing y equals, say, x squared to, which you know should look like this, compared to y equals x plus 1 squared. That one would shift over here. So the point that was at 0 now shifts to minus 1. It'll shift to the left. This guy shifts right by k units. Use y equals x squared again. So it goes through the origin. If I look at y equals x minus 1 all squared, so I just subtracted 1 from all the x's, that'll shift to the right by 1 unit. Worth mentioning that you can apply multiple transformations at once. We're going to see a wonderful application of this when we look at trigonometry and we start graphing some trig functions. So I can start with a function f of x, and I can decide to shift it. You know, horizontally by 1 unit. Then I can say, oh, I'm going to stretch it, and then I'm going to add 3, right? So I can do a bunch of things all at once, and the graph will move around and change itself based on what I'm doing here. And sometimes students get confused on how to actually apply this, but the rule is you apply transformations in the order of PEMDAS, it turns out. In other words, you would do what's in the parentheses first. So if you know what the original graph of a function looked like and I ask you to graph this function, you would first shift to the right, then you do multiplication, so then you'd stretch it by vertically by 2. Then you do addition, so then you'd shift the result up. Right? So sometimes if you do things out of order, you're going to get the wrong graph. You would apply whatever we're doing to the function in the order of PEMDAS. So like I said, that should give you some intuitive grasp of how to get new graphs from old ones. So now that being said, I want you to know the glossary of graphs that you should have in your head, pretty much have memorized. And so whenever you have one of these graphs, a transformation of one of these, you should exactly know in your head what the picture looks like. And then your job is to just graph that picture through the right points, right? Similar to how we looked at parabolas, right? So I know the shape is either going to be this or it's going to be that. And I'm just using these numbers to tell me where do I draw this, right? So in that way, a lot of the graphing that you're going to be doing should be done kind of like that. You have these templates in your head that you're trying to fit the numbers on. And so I'll tell you now the graphs I expect you to know. And I asked some of them on the very first quiz that we have in this class. So something like, well, first of all, any line, any quadratic. But I'll specifically mention x squared and x cubed later because I want to know about it. I want you guys to, we're going to apply it to something else. But you should also know things like y equals the square root of, I'll just put it, y equals x. You should definitely know that without even thinking about it. Y equals x squared. You should definitely know that without even thinking about it. Y equals x cubed. You should know that without even thinking about it. Y equals the absolute value of x. You should know that without even thinking about it. What else? There are functions that I haven't told you about. Do I need to know that? Another popular one. Y equals the square root of x. You should know what that looks like without even thinking about it. So you're going to have to know exponentials. Didn't tell you about that yet. You're going to have to know logarithms. Didn't tell you about that yet. So far, I think that's basically it. You should know how to draw any line in any quadratic, but you really should have these pictures kind of burned into your brain where you can draw them without in almost zero time. I think that's all you kind of know at the moment. We'll get some new graphs later, some standard graphs for you to know. By the time you get to the end of this class, there'll be more graphs added to this list. You're going to need to know about exponentials and log graphs and trig functions. What is a standard sine graph look like? What a standard cosine? What a standard tangent looks like? They're going to be more added to this list. But at this point, I think you should know that stuff: radicals, polynomials, absolute value. Yeah. So those are what you should know, and a lot of graphs you can get just by shifting these. Now. I don't think I want to waste more time on these examples. Let's get to something a little bit more sophisticated. And we're going to talk about graphing polynomials in general now. Important steps. One, finding zeros. So there's something called the zeros of a function, or the roots of a function. AKA. I mean, that sounds fancy, but it's not really fancy. It is quite literally a synonym for x-intercept. So that'll tell you exactly what the zeros are, or what the roots are, or what the x-intercepts are. It's just the x values where the function hits the horizontal axis, right? We need to be able to find these. It turns out that the function will hit the horizontal axis whenever the f of x is equal to 0. So this is x values for which f of x equals 0. Right? So obviously to find the zeros of a function, or to find the x values of a function, you need to know how to solve equations, because finding the zeros involves you solving equations. Okay? So I pretty much told you how to solve a lot of equations already, so I don't really need to express more about that at the moment. Another idea that you want to know is you need to know how to test intervals. So this is kind of like what we did when we were solving inequalities. You plug in numbers in between the special numbers that you just found to figure out, is the graph positive or negative, right? So plug in numbers in between the zeros to see if the graph is above or below the x-axis. So that's going to show you roughly where the position is. And 3, which I consider optional, but a lot of people make a big deal out of it, and your textbook makes a big deal out of it, so I'm going to tell you what it is anyway. But with those two, you can sketch a graph. But a lot of times, people often like to talk about end behavior. So this is how the graph behaves at the ends. Okay? So now, the quintessential graphs here is you want to think of a graph like y equals x squared versus y equals x cubed. Now, what do you notice about the ends of y equals x squared is that both the ends go up, right? And it turns out that in general, if you have the highest power of a polynomial, the x to the n where n is even like it is in x squared, the ends will go up. And the only thing that changes is the larger n gets, the wider these graphs will get. So, so if this guy here is x squared, then your x to the 4th will have the same behavior, but it will be a little bit wider. And your x to the 6th will have the same behavior, but it will be a little bit wider. But basically, all guys with even powers, both ends will always go up. So that's something that you should notice. And so that's the idea with end behavior. When you look at the x cubed graph, a different story happens. One side goes up, the other side goes down. Right? X cubed is like that, right? Well, this one's like, I don't know, like Michael Jackson and Elvis. I don't know what the right thing would be, but so if you have x to the n where your n is odd, then you'd expect one side to go up and the other side to go down. And again, if you change the powers, it's just you're changing the width of the thing, but that's important. And of course, because we know about transformations, we automatically So we have the following. You have y equals x to the n even. Then you expect both sides to go up. If you have the negative of x to the n, where n is even, you expect a flip in the horizontal, so you would expect both sides to go down. If you have y equals x to the n is odd, you expect one side to go up, the other side to go down. Whereas if you have y equals minus x to the n is odd, then you'd expect the opposite to happen. The right side to go down and the left side to go up. So this tells you what's happening far at the ends. So your graph can do whatever it's doing in the middle, but what you want to realize is pay attention to the highest power. And we're thinking of x to the n here as the highest power will have the control. So I can tell you, okay, we're going to plot a graph, it's x to the 7th plus blah, 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 and I can say a whole bunch of blah, blah, blah. But if x to the 7 is the highest power, I know the graph won't end up looking like this at the ends, it'll end up looking like one of these. If it's x to the 7th plus blah, 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 then it's positive 1 times x to the 7th. It means that the right side of your picture should be going up to infinity, and the left side should be going down to infinity. If I said, oh, the graph is y equals minus 3 x to the 7th plus blah, 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 doesn't matter what the blah, blah, blah is, it means that the right side should be going down in your picture and the left side should be going up in your picture, right? So pretty much you're going to pay attention to the highest power. And the highest power is going to tell you what the behavior is. And this kind of idea, this kind of notion, when you're looking at it, it's called end behavior. And so some people might have you write down the end behavior, but I won't. But they might describe the end behavior to say something like, well, as the x is going off to infinity, the y would go off to infinity, right? So here's like as your x values are getting big, your y values are getting big. And here as your x goes off to negative infinity, the y value also goes off to positive infinity. Whereas this one I would describe it as x goes off to infinity, the y goes off to infinity, but as x goes off to negative infinity, the y also goes off to negative infinity. Right? So that's the difference between evens. The even powers always stay positive in the y, whereas the odd power is going to switch on you once your input switches signs. So that's called end behavior. That's the idea. So let's get some graphs. Okay, so we're going to start out easy and probably end with something a little bit harder, like what was on the bonus problem of your test. Example. Use these ideas to sketch the following. Okay. Well, this one I'm just throwing in to see if you remember what we did last week before the test. It's a quadratic. Let's do those first. So, first we find the zeros. That's just another way of saying find the x-intercepts. How do you find the x-intercepts?
So y
set y equals 0 and solve for x. So this means set y equals 0. This means you have 2x squared minus 3x minus 2 equals 0. How do I solve that for x? We'll try to see if it factors. What would be the factors here? 2x and x. What numbers do you put here? Yeah, it has to be a 1 and a 2. Where you want to put the 1 and the 2? Who's on the right? The 2 and the 1. So now you look at the outside. That gives me 4x. The inside gives me 1x. I want it to be a minus 3. So I can make that minus 4 plus 1. That'll give me the minus 3. So that factors. So this means that the x is minus 1/2 or 2. Now the y-intercept is also always something that you'd want to graph. So this means set x equals 0. And you'd find that the y here is minus 2. Now we know about quadratics, what shape this is going to be. It's supposed to look like that. But if we even use the idea that we had here earlier, so where are our x-intercepts? Minus 1/2 and 2. So another way you can look at this is you look at the highest power. You notice that it's even, so you automatically know that both sides on the ends are going to go up. You can plug in a point in between here. So we already know about what's happening on the left and the right. I don't know what's happening in the middle, so I'm going to plug in a point somewhere in the middle here. 0 was a nice point to plug in, which we actually already did. So that tells me that the graph should be down here. So I know that the graph is going to look like that. Which we kind of already know, but I wanted to emphasize using these ideas because we're going to expand on it. Now the x cubed is a little bit different. But we're going to go through the same process. Find the zeros, the x-intercepts and the y-intercepts, and then we're going to plot the b. What are the x-intercepts? How would I find them? Set y equals 0, and I want to solve for x. How do I solve that for x?
You take out one factor out, right?
Factor, right? So
Yeah,
x would be the common term. I've left over with x to the minus 4. What is that?
The difference of perfect squares.
That's the difference of squares. So I have 3 zeros, aka x-intercepts, and then I find the y-intercepts, and that means that'll just be y equals 0. So I plug in x equals 0. So now I can come over here, and I can start to sketch the graph. I'm going to erase this. So let's start by sketching the graph. So we're here. So first thing we're going to do is we're going to plot the x and y intercepts. So the x goes between 0, 2, and minus 2. Now, because of end behavior, the highest power here is a cubed, and it's positive. So what do I expect to happen at the ends? The right side should be going up, and the left side should be going down. So I don't need to test numbers over here. I already know what's happening over there from end behavior. So all I need to do is test these two intervals here. So what I'm going to do is I'm going to pick a random number, like -1, and I'm going to plug it into the function. Now, pro tip, it's always better to plug in into the factored form. Just make sure that when you're actually factoring, you don't like divide out a negative sign or anything like that, because then that will be bad. Okay. So you just factor out the negative and leave the negative sign there. Okay. So The reason why I'd like to plug it into the factored form is because the actual value I get, I don't actually care about. I just really care, is it positive or negative? Is it above the horizontal or is it below the horizontal? So we're going to take -1, put it here, here, and here. So put a -1 here. That's a negative number. That'll give me a negative number. Put -1 here. -1 minus 2 is also a negative number. Put a -1 here. That will give me a positive number. So I have a negative times a positive, which overall gives me a positive number, which means I know the graph should be up here. It should be above the horizontal. Pick another random point over here. Let's say I pick a +1. Plug it in here. That will be positive. Put +1 here. That will be negative. Put a +1 here. That will be positive. Overall, this gives me a negative, and so I know the graph should be down here. Okay? So pretty much I know the graph needs to pass through those coordinates. It should be down here, then up here, then down here, then up here. Right? And so now I can start to actually sketch the graph. Now the thing with polynomials, they're very nice to graph. They're very smooth and curvy. And so we pretty much draw a smooth and curvy thing that has this behavior. So I'm going to go like that. So I know I should be down here, and this end should be going down. I need to touch this, and I tested that I need to go up. But then I realized, oh, I need to turn around to hit that. So I'm going to turn around. And once I'm here, I'm like, okay, where should I go now? Oh, I should be down here. So I'm going to go down. And then I'm like, oh, I need to come back up to hit that. So I'm going to turn around. And then I know, oh, I should be up here. So I'm going to continue. And that is the picture. Right? So X marks the spot. I'm going to just plug in numbers to know which position I need to be in each interval. Should I be up or down? And I know what the ends are. But the reason why I said the end behavior is kind of superfluous, you actually don't really need that idea, because you could just easily just try a number over here. You plug it in and realize that the graph is up here. And if you plug in a number over here, you realize the graph is down here. So you could just know, find all the intercepts, test every interval, and you get the same thing in the end. So yeah, the graph of this would look like an end. So that's one pro tip that you want to know about. One other thing that you should know, and this is just to kind of double check yourself, once you've drawn a picture that you think is the picture, a polynomial can have at most, right? This is the maximum, it could possibly have less. One less turn than the highest power. Okay. So remember I was saying I was graphing this, and there were times when I was like, oh, I need to turn around. Oh, I need to turn around, right? If I have a graph where the highest power is a 3, I should have that inclination at most 2 times. If you turn more than 3 times, you're not graphing the cubic anymore, right? Highest power is 3, I can have at most 2 turns. I could have less, but at the maximum amount of turns I would have is 2. Here was 1 turn, occurred here. Here's another turn, second turn, occurs here. There are no more turns. Once I made those 2 turns, the graph just keeps going, doing what it's doing, right? So if I went, oh, turn here, and then I turned again, it's not a cubic anymore. You're graphing something else. You made a mistake. Danger, Will Robinson. System's failing. Right? You need to know. So once you actually draw a picture that you think is a picture, double check. Okay, the highest power is 3. I should have at most 2 turns. Okay, I also know that it's odd. The end behavior should go in here. So you should kind of be able to spot if anything's going to be wrong with your picture. And so that's what the graph of this function would look like. Any questions?
Yeah. How do you determine how high each curve or how low each curve was?
Oh, you don't. And in pre-calculus, you can't. So that's something that you'd actually answer that question in calculus. Okay? So it turns out that there is no general formula to find the peak or the depth of some curved term. Calculus helps you do that. So at this point, don't worry about it. We're just doing a naive sketch. Right, so when you get to calculus 1, you're going to do curve sketching again. You're going to do it in a lot more detail. They're going to expect you to be able to identify what these coordinates are. Also, down to how you're curved while you're drawing something is going to be super important to them. They're like, oh no, you should have shaped like a smiley face here and you didn't, like, it's wrong. Right, so you're going to graph in a lot more detail. For us, this is as much detail as we want to be in. So for us, we're just doing very naive sketches all the time. Which is another reason why I'm saying, like, the kids who like to do this, feeling like, oh, it has to be exact. No, it doesn't have to be exact. Just, I know it should be up here. Just go as high as you want, and it's not going to matter. Okay? It has to look like an N. Is the important thing. No sharp corners or anything like that, because polynomials don't behave that way. They're very smooth functions. And believe it or not, smooth is a very technical term. Again, in calculus, you're going to learn what smooth means in a mathematical context. But polynomials have that property. They're smooth. They don't have any jagged edges or anything like that on the picture. Let's do it again. Let's do it for C. So this is next to the fourth graph. Okay, so y equals x to the fourth minus x squared. So without me graphing anything at all, I automatically kind of have a picture in my head. I know that the ends of this thing should be going up. I also know that I should turn at most 3 times. And I'll have at most 4 x-intercepts. Right? I know all that before I even graph the picture. So if whatever I graph does not have those properties, I know something is off. Okay. But we just want to sketch this guy. So the first thing we're going to do is we're going to find the zeros, which are the x-intercepts. Means you set y equals 0 to solve x. Here x squared would be a common term. Here you have x squared, x minus 1, x plus 1. So here, x equals 0, x equals 1, or x equals minus 1. I also have the fact that the y-intercept is y equals 0, just by putting x equals 0. So now I'm going to graph this. Let me put the y-axis right on this line. First thing you're going to do is you're going to put in all these intercepts that you found. 0, that's the x and the y-intercept. Minus 1, positive 1. I automatically know that the ends should go up here because it's an even power is the highest power. I'm not sure what's happening in the middle. So what I would do is I would test the numbers. Okay. You'll notice that even if you plugged in a number over here, you'd get a positive number, it would be up here. And if you plugged in a number over here, you get a positive number, it would be up here. Plug in something in the middle. Let's say minus a half. If you square it, it's going to give you a positive number. Plug in minus a half here, you get a negative number. Plug in minus a half here, you get a positive number. So this is negative overall, so the graph would be down here. Pick a random number in here, like positive a half. Square positive a half, you're going to get a positive number. Plug in positive a half here. If you subtract 1, you'll get a negative number. Plug in positive a half here, you get a positive number. So it's again negative, so the graph should be down here. So I'm going to draw a very smooth, wavy curve that's up here, then down here, stays down here, and then goes back up here. And it touches these 3 points while doing that behavior. So you'll realize it'll end up looking like this. So I'm coming down because I have to hit that point. Okay, boom. Where should I be? Okay, I should be down here. So let's break through, go down. Oh, but now I have to turn around to hit here. So I'm going to come up, I'm going to hit here, boom. But oh, I should be down here. So I have to turn around right again and come down. But oh, need to turn around to hit that. So I'm going to come back, boom. Okay, where should I be now? Up here. And that's a W. Find all the x-intercepts, find the y-intercepts, test when your graph should be above and below, and from that you just follow the x's. X marks the spot. You need to be in the location where these guys are, and you need to make sure you're passing through these points. You'll notice here, this one has 1, 2, 3 turns. That's good. That's the most amount of turns I should have for an x to the 4th graph. And both ends are going up. Yeah, so I'm pretty confident that this is a graph. Now, you might notice here how this is shaped, kind of like an upside down x squared, right? And that's intentional. Again, if you just have the idea that you have to avoid a sharp corner, you kind of figure out that you have to do that. But one way to also do that is to notice the kinds of zeros you have. Notice that x equals 0 looks like a square term. So it means when you're passing through that point, you should kind of look like a square term. And that would be true if this was any even number. You'd look like this. You'd look like an x squared, essentially. Right? If over here was an odd number, it turns out that you pass through it. If it's a 3 or higher, you kind of curve yourself like an x cubed would as you pass through the point. We'll see examples of that pretty soon. I'm not sure if the next one is not an example like that, but the problem on the test is an example of that. Any questions on this one? Any ideas not fitting in? Now, sketching things are super important. I know in your test, there's like going to be one question that asks you to sketch something, but it's an idea that will help you in a lot of other contexts as well. Especially in like calculus and calc 2 and calc 3. But you need a good bit of sketching knowledge in pre-calc as well. There are a lot of problems where until you draw the picture, they're very hard, but then you draw a picture and it's like, oh, this is what I have to do. So let's do D. Okay, now I'd like volunteers to tell me how we're going to tackle D. I want you to graph x cubed plus x squared minus 9x minus 9. Okay, that's the first thing we want to do. Yep.
Factor by grouping,
Why?
because there was 4 terms.
Okay. But why? Why should we be factoring it all?
How to get the zeros.
To get the zeros, you need to know, first thing I want to do is find the x-intercepts, right? That leads you to the fact that I need to solve this equation. Then you know, to solve any equation higher than a linear equation, what I do is I factor. So that's where factoring will come into play. And so now you wonder, how should I factor this? You know all the steps to factor. First thing you're going to look for is common terms. Don't have any here. Next thing we're going to look, if there are 2 terms, we can use difference of squares or sum or differences of cubes. Not what we have here. If there are 3 terms, you can use the AC method or the method that we use for factoring quadratics, the trial and error. Not what we have here. If you have 4 more terms, you should try factor by grouping. So, as he said, factor by grouping is what I would try. So factor by grouping means we're going to group them, pair them off, and then try to factor common terms out of each pair separately. Now, the hope is that what's left over in the parentheses will be a common term afterwards. So, common term between these two.
X squared.
X squared. So I'd be left over with an x plus 1. Common term between these two. Minus 9. So I'd be left over with an x plus 1. Notice that now x plus 1 ends up being a common term. I can factor that out. Now we notice that's difference of squares. So this means x equals -1, x equals 3, or x equals -3. The y-intercepts, y equals -9, because if I plug in 0, 0, 0 for x, -9 is going to be the answer. And at this point, I'm going to draw in my axes. I'm going to plug in these, plot these guys here. So we have one at -3, -1. We have one at 3. And we know the y value passes through -9, which I'm going to kind of make here. Okay, so that's the first thing. Now, highest power is a cube, so I already know what the end behavior is because there's a positive number in here. So I know that the right side should be up here, and the left side should be down here. The question is, what happens in the middle? So I'm going to plug in random numbers. Let's pick a -2 between here. I can pick a 0 between here, which I already know that's got to be down here because I already picked the y. And we actually already know there. So ultimately, when it comes down to it, I have to only test one interval to figure out what this particular graph looks like. And so I would look for -2, plug in here. -2 plus 1 gives me a negative number. -2 minus 3 gives me a negative number. -2 plus 3 gives me a positive number, which means that the graph should be up here. So my graph needs to pass through this point, and that point. Then it needs to be down here, then up here, then down here, then up here. So now I'm just going to draw a very wavy curve that does that. So it's going to look like this. It's a picture. There's another end. That should pass through -9. Just put that here. So you won't need to sketch it any more accurately than that, not for a pre-calc class. You just need to know the general kind of shape that your function will go through. Now let's look at the problem that was on the bonus to the test. So we already know the basic ideas, right? I just told you those, so we're going to apply it to a little bit more much more of a complicated example. So this is test 1 bonus. I think I wrote it down here. Yeah, okay. So it was, I wanted you to graph 2 times x plus 3 squared times 2x minus 1 cubed times x squared plus 9. Okay, so a couple things we need to know here. First, we need to know what the highest power is because that's going to tell me about the end behavior. So, in other words, the highest power is going to be the sum of all the powers, right? Because remember when I multiply out, laws of exponents says if I multiply the two same x's, I'm going to add the powers. So I'm going to just add up all the highest powers. I'm going to have an x squared from this one, an x cubed from this one, and an x squared from this one. So the highest power is going to be like an x squared times an x cubed times an x squared. So that's going to be what? I just add these. So this is an x to the 7th graph. Now, once I know it's an x to the 7th, I automatically know what the end behavior is. So let me start writing that in. So once I realize, oh, I'm looking at an x to the 7th graph. Aha! I know the graph needs to be down here all the way to the left. It needs to be up here all the way to the right. Now let's find the specific points. The next thing we want, and of course here, you should notice that the x's would be positive. Right? Now specifically, if you multiply out everyone here, you'd have a 16x squared, but that's not really important for you to know. What's really important for you to know is it a positive or a negative, and what's the highest power? You're going to get a positive x to the 7. Now, the next thing we're going to do is find the x-intercepts. So that means we're going to set y equals 0, solve for x. Now the nice thing about these problems, the nice thing about this particular problem, is it was already factored for you. So now all you have to do is you have to pick the x's that make each factor 0. So what would make this 0? X equals minus 3. What would make this 0? X equals positive 1/2. What would make this 0? Nothing. That's never 0, right? Your x squared is always going to be 0 or bigger, and then I'm adding 9. So this part of the expression is always 9 or bigger. It's never going to be 0. So there are only 2 x-intercepts. Then I'm going to look for the y-intercept. So this means I set x equals 0 and solve for y. So my y would look like 2 times 3 squared times minus 1 cubed times 9. So this is going to be, well, this is just going to be a negative sign. So this is 9 times 9, 9 nines 81. 81 times 2 is what? Huh?
162.
So 162. Minus 162. Okay, great. So let's start counting. 1, 2, 3. Yeah, okay. No. I'm going to pick a random point. I'm going to call it minus 162. Right? I'm not going to spend the entire exam counting to 162. Okay. So now I know my x will cut through minus 3. And it will also go through positive 1/2. I know I should be down here. And I know I should be up here. And I even know I should be down here. So I actually don't need to test any more intervals. We already tested everything. Okay. So here's a little bit of a nuance. You can notice here that this guy came from here, which was a square. So you kind of already expect that when you're passing through this 3 here, you look like an x squared. And the guy that gave us a 1/2 looks like a cube. So it means when you're passing through here, you want to look like an x cubed. So a little inflection going there, another technical term. You don't really have to worry about it though. But that's kind of it. I mean, we don't have to test anything else. Like all the intervals have been tested. So from end behavior, we know it should be down here and up here. And in the middle, I would have picked 0 as the number to test, but we already tested that to find the y-intercept. So there's nothing else to test. So at this point, I'm just going to sketch the curve. I need to be down here. I need to come up to hit this. Then I need to go down to hit that. Then I need to come back up to hit this. And then I need to go up. So that's what I'm going to do. Do a little bing. I'm just going to look at that. That would be the graph. Any questions on this one? Yeah.
I'm confused as to why 3 isn't an x-intercept as well.
3 itself?
Yeah. From the x squared plus 9. I thought that that would be plus or minus.
No, x squared minus 9. It's a sum of squares, not a difference of squares. Right. Because if you said x squared plus 9 equals 0, that means that x squared would equal minus 9. And so to find x, you have to take the square root of minus 9.
Oh, got it.
That's a complex number.
Got it.
So it's not in a place where we can see it in the first place, right? It's imaginary. Yeah, so here we just have the minus 3. that's graphing. And that's pretty much all you need to know about graphing. We don't need to get any more specific than that here. In Calc 1, you're going to, again, like I said, you're going to revisit graphing, and you're going to do it in a lot more detail. Right here, we can be kind of lazy. So it's just need to know roughly what position everything is. Try to put your numbers to scale somewhat, but hey, if it's not a terrible tragedy. And yeah, just know the locations where you should be. You should be up or down, and that's basically it. Otherwise, if your graph is very simple, something like, I don't know, say y equals x plus 1 all squared minus 3, then I just use the transformations idea. I know what x squared looks like. I'd shift it to the left 1 unit, then shift it down 3 units. And then that would be the picture. But once you know how to find zeros, test the intervals, you know how to graph anything else, any polynomial that is. There are other graphs that are a little bit more complicated. But we won't deal with that. Yeah.
Why did you substitute each term when you said x equals 0?
Here? No, here I was finding the y-intercept. So the y-intercept means you set x equals 0 and you solve for y. So I didn't substitute, I substituted x equals 0. I replaced x with 0 everywhere. And then I would have gotten this. Other questions before we move on? So now what I want to talk about is inverse functions. Another topic you really visit in Calc 1 yet again. But we do need to have some background. By the time you get to Calc 1, your professor will expect that you have some background, an idea of what an inverse function is in the first place. Now, there are a lot of things that you need to know about a function before you can determine it has an inverse. Technically, you don't need to know these things in pre-calc, but it would kind of be really bad of me not to tell you about them. So what I'm going to do is, I'm going to tell you the stuff that you need to know. And then I'm going to say, by the way, here's some background that your Calc 1 professor is going to think you know, but you probably would have ignored it in pre-calc. So we'll probably do it that way. So there are a couple things that you guys need to know about inverse functions. You generally need to know what they are, what they do. You also need to know how to compute one. So if I give you a function, you need to know how to find its inverse function. And you might need to know how to do a naive sketch of it. Probably not. But I'll talk about those three things first, and then I'll tell you some background that it will be good for you to know. That's going to be very important. If not now, it will be important in the future if you need to go in further mathematics. Okay? Because sometimes you need to know, how would you know that something has an inverse in the first place? In this class, you won't have to know that. We're just going to give you a function. We're going to tell you it has an inverse. Find it, right? But there are times when you're not going to be sure if that thing even exists. And so how would you go about figuring out that it even has one in the first place? And that's a whole other story. So I'll talk a little bit about that, but for now, let's actually just talk about inverse functions. So we're going to get down to the nitty-gritty, right? So the pre-calc treatment of inverse functions, I'll fill in some gaps a little bit later, but it's kind of okay if you don't remember the gaps, but you should. Especially if you're going further, especially if you're like a math major, you want to be a physics major, you want to be an engineering major. The fluffy stuff you need to remember. The rest of you can kind of forget it. Just remember what I'm going to tell you now. Okay. So, suppose, let's say f is a given function. So you have some function you're considering. We say g of x is an inverse of f of x if G undoes the rule done by F. So what do I mean? Okay, so here's a picture of what I mean. So let's say here's some value. So this is the domain and codomain of F. And by the way, G must be another function. So it'll have to obey the function rules. And that's where the kind of details come in that a pre-calc student doesn't have to worry about. But I'm going to tell you guys anyway. So let's say F, okay, this is in the domain of F. And here would be the codomain of F. So F is going to take someone and it's going to do something with it, and it's going to move it over here, and it's going to do something. F of X, right? It's going to perform some rule. Okay. Now, what I'm saying is, what if there's another function that reverses this process? Okay. So let's say I can come up with another function where this is its domain, right? So let's say I think of this as the domain of the function G. And G is a function that literally, whatever F does, it'll do it, take backsies, right? So like, it'll take that guy and it'll bring it back exactly to the original guy that F moved it in the first place. So F is going to move that, G will move that. And if I can find a function that does this for every single input, then that function is called the inverse of F. So, more specifically, if F is a function with domain A and codomain B, then G is a function with domain B and codomain A. Let's swap these. I'm so used to writing the A before the B. A. Then that's the picture of what's going to happen, but you don't always have the luxury of being able to draw a picture of the thing that we're telling you. So this basically says, if F does something, and I plug that into G, it's going to undo what F did. So it means that G of F is going to be the original input. G of F of X is going to just be X. And this will happen for all X in B. And at the same time, if I do the composition in the reverse order, F of G of X, which is the same as saying F G, will give us the original output X. And this here, X is living in A. So we say functions are inverses of each other if, when you plug one into the other, you just get the original input back. Because one function does something and the other function takes it back. So you'll always get the original guy. And this happens for everybody. Right? Anytime that happens for everybody, we say we have an inverse function. And we can say F and G are inverses of each other. Because it turns out, if F does something and G undoes it, then also by the same token, if G does something, F is going to undo that as well. So it turns out once you know this guy's an inverse of that guy, then the relationship is reflexive, right? So if G is an inverse of F, it automatically means that F is also an inverse of G. And so we might use the phrase they're inverses of each other. So once they can go in both directions, we say they're inverses. So pretty much, if you have two functions, and if someone gives you two functions and they ask the question, are these inverses? All you have to do is plug one into the other and see if you get X as the result. And you do this in both orders. So here's another way you can think about it. So if y equals f of x, then what happens is you take x, f would move it to y, g is going to take y and move it back to x. So you can think of g switches x and y. Right? So it kind of flips the function around. And we're going to actually use that to compute the function. Like I said, being able to compute one is one thing that you're going to want to be able to do. Some notation. You'll see this from time to time, pretty often. If g is the inverse of f of x, then we can write g of x equals f power minus 1 of x. And this is a very special notation. It doesn't literally mean the power of minus 1, like it doesn't mean a reciprocal. It doesn't mean 1 over. It's just, that's the notation for it. Right, f to the minus power, it's called the inverse. And so this is read, it's read f inverse of x. So it's just a notation you can see. It can be particularly confusing in some areas like trigonometry, and so we come up with alternative notation, but when we get there we'll talk about that. Okay. So in other words, if I take f of f inverse, it will give me x, and if I take f inverse of f, it will give me x. When you get to calculus, you're going to use that equation to derive something that you'll need there, but we'll stop there for now. Okay, so now, to compute f inverse of x for a given x, f. If it exists. Turns out not all functions have an inverse. I'll tell you specifically which ones do and which ones don't next time. But let's pretend the function has an inverse. How would you go about actually computing? Well, by the above, what you should note is the input of f is the output of f inverse and vice versa. Right? That's what you'd notice from the pictures I just drew. So this means to compute f inverse, switch x and y and solve for y. And that's it. So again, it comes down to you being able to solve equations. So we spent a long time solving equations, from what I remember, just because it's important. There are a lot of things that we only know how to figure out by solving equations. Where did I put my examples? Okay, let's look at some examples. Find the inverse of the following. I believe this was on the test as well, in the bonus section. So let's do several of them. First one's kind of easy. if 7C. Not sure I want to do this one. There's a star on this one. So that one has a restriction that I'm not sure I'll tell you about today. I'll probably talk about this one next week. Because technically this one does not have an inverse. How would you recognize that it doesn't? I'd have to talk about that. And what can you do when you recognize that it doesn't? Because sometimes you can kind of salvage it. So that would be a good illustration of what the kind of thought process you'd have to go through to create a function like the sine inverse function or the cosine inverse function. Because it turns out those functions do not have inverses if you take them in their entirety. You kind of have to chip away a piece that is representative of everything and then do some trick with that. So that one's that kind of. Or maybe, I don't actually have the test with me, so maybe we can also throw in the example from the test. But if you think you know how to do this, you can start on those. Let me just pull up an example, an additional example here for you guys. Yeah, so in the test there was 2x plus 3 over 4x plus 4. From test, the bonus section. Yeah, find the inverse of blah. Okay, we're gonna do all these guys. Look at 8. So let's get used to the notation. So I'll write this as f of x equals 1. I'll write it down in the other notation. So let's say this is f of x, which is that. So what you notice is that you write for inverse, switch x and 1. So that means we have x over here, and you literally switch the places of x and y. Everywhere you see an x, you write a y instead. Everywhere you see a y, you write an x instead. And so now, solve for y. Because it's like you want the input to become the output, and then you want to write the function in terms of the output. How do you solve for y here? Tons of ways you can do it. Like cross multiply. This one is. And that's it. There's nothing else to do with this one. The f inverse function would be that guy, 1 over x. Now this is a strange kind of function. It is its own inverse, which happens from now and then. And you can even check this, right? So if you look at f of x is 1 over x, and someone tells you f inverse is also 1 over x, you might be like, that's weird. How is it its own inverse? Well, you can actually do the check. If I take f of f inverse of x, that's like me taking 1 over x, and then keep, change, flip gives me x as the answer. It does the job. So if I have a function that all it does is take a reciprocal, if I want to reverse that, just take the reciprocal of the thing I took the reciprocal of in the first place, right? So if it turns 2 into a half, just flip a half again, it'll turn it back into 2, right? So this is a function that is its own inverse. Kind of a strange thing, not all functions have their own inverse. Not all functions are their own inverse. But that's an example where that happens. So, I just want you to get the ideas with these. More than likely, anytime I ask you a question like this, it's going to look something like C or E. So here f of x equals y equals x to the fifth minus 7. Or inverse. Switch x and y. This means y, I'm going to put x. Where there's an x, I'm going to put y. I'll solve for y. How would you solve this equation for y? Add 7 to both sides, right? You want to isolate it, right? So now what? The fifth root, right? You can raise both sides to the 1/5 power. Laws of exponents would tell us that that will cancel. So I would just take the fifth root of both sides. Notice that when you take an odd root, you don't get the plus or minus, right? It'll keep the same sign. And so that means I can say here, f inverse of this function is the fifth root of x plus 7. So if I have a function that does this, raise something to the fifth and then subtract 7, it turns out to reverse that rule. I'm actually going to take x, add 7, and then take the fifth root. And this is something that you could actually check. I won't do this for all of them probably, but this one's easy enough for you to check. So check B. Okay, so what would f of f inverse look like? This means I go to the f, everywhere I see x, I'm going to replace it with f inverse. So this is going to say f inverse to the fifth power, and then I'm going to subtract 7. That means I'm taking the fifth root of x plus 7 to the fifth power, and then I'm going to subtract 7. Well, raising the fifth root to the fifth power, those will die. I'll get x plus 7 minus 7, and I get x. Okay, so far so good. Go the other way. If I take f inverse of f of x, that means I'm going to go to the inverse function, and everywhere I see an x, I will instead plug in f of x. If I plugged in f of x, this would give me x to the fifth minus 7 plus 7. Those 7s would die, and I'd get the fifth root of x to the fifth, and then those would cancel, and I would just get x. And so if I plug one into the other in either order, notice that I get x as the result. That means, okay, we did the right thing. That's the inverse function. Let's get C. Okay, suppose our function is y equals 1 plus x over 1 minus x. So we're assuming it has an inverse. Now we want to find it. How do we find it? We switch x and y. Then we're going to solve for y. So this means I'm going to start with x equals 1 plus y over 1 minus y. Okay, how do I solve that for y?
Multiply both sides by 1 minus y.
I would start by multiplying both sides by 1 minus y. Now what?
And with the parentheses, so it would be x minus xy with 1 plus y. You want to bring the y on the right-hand side of the equal sign over, so minus y on both sides.
Do this?
Yeah. And you bring the x the other way.
Notice, remember when you're doing an equation, your goal is to isolate the guy you want to solve for. sure, he's over here, but he's not isolated as y equals. So what you do is you move this over and you multiply out. So now you expand everyone, and we just want to gather all the people that have y's in them. So I took this y and I moved it to that side, so that's the minus y. And then I took this x and I moved it to that side, so that's the minus x here, right? So I wrote it without fractions, right? So I multiply both sides by the LCD to spread everything out. Then expand everybody, and then I'm going to gather all the terms that have the y's in them. So that's what I'm doing now. Now the reason why I would do that is because now y is a common term on the left side, which means I can factor it out. And so now to isolate the y, I can finish off by dividing both sides by this. And that's actually good enough for the inverse function, but the negative in front here, you might want to factor out the negative, and so you probably write it as something like x minus 1 over x plus 1. And tons of ways you can think about getting that. You can think of it as just me multiplying and dividing by -1 to make it a little nicer. So the bottom, -1, we'll just change all the signs to positive. In the top, it will turn into positive x minus 1. So it's nice to get the coefficient of x positive, if at all possible. It's a cosmetic thing. It's not super. That's the idea. And you can verify for yourself. If I were to take this thing and plug it in here and here, it'll all simplify and I'll get x as the result. And vice versa. If I take this thing and plug it in here and here, it'll all simplify and get x as the result. You can do this at home. I'm skipping this one, we'll talk about it next time. Let's do the example that was on the test. Although honestly, it was very similar to this one. It's not going to be. So let's say f of x equal y equals 2x plus 3 or 4x plus 4. Did anyone actually try this one? Okay, so do you remember what your answer was? Okay, well if you remember what your answer was, now we'll see if it was right or not. So you can be like, yay! Or you can be like, damn it. Okay. So we're going to switch x and y and solve for y. So that means I'm going to get an x equals a 2y plus 3 over a 4y plus 4. Very similar to that one. I'm going to multiply both sides by 4y plus 4. And I get that. Now I'm going to expand the parentheses, so I'm going to get 4xy plus 4x equals 2y plus 3. Now I want to isolate the y's. So all the terms with y's, I'm going to bring it on one side. All the terms without y's, put them on the other side. So this, I'm going to gather the y's on the left side. So this guy has a y in him, so leave it. This 2y, move it over here, so it becomes minus 2y. This guy doesn't have a y, so get out of here. I'm going to move it over here. This 3 doesn't have a y, so he stays where he is. So that's the next step. Now you realize that y is a common term, so I can factor it out. And now I can just divide both sides by that. And that's your answer. That's the inverse function. So your answer would be f inverse of x is the function 3 minus 4x over 4x minus 2. And again, you can check this. You take this whole thing and put it here and here, it'll simplify and you'll just get x. Take this whole thing and put it here and here, it should simplify and give you just x. I think we'll stop there for now. We don't have 2 minutes, not much to do anything. We'll talk a little bit more about this, but next time we'll also try to get into dividing polynomials. So if you want to review long division of polynomials or that kind of stuff, the rational roots theorem, that's what we're going to talk about next time. And that'll probably be also what I would put on the bonus for the quiz.